So for sample exercise 16.20, I had to look up the electronegativity of AS and O. Oxygen has an electronegativity of 3.44, AS 2.55. Therefore, O is more electronegative, so H2O will be on this side. And ASH3 will be here. So NaH is the weakest acid, followed by ASH3, followed by H2O, and HI is the strongest acid of this list. Okay, let's try letter B. So B, they look like they're oxyacids. So then, if they have their oxyacids, you pick the one with the most oxygens. So this one has 4 oxygens, and this has 4 as well. But the central atom's different, the S and the Se. I looked up their position on the periodic table. Since S is closer to the top, that means it's smaller, it is more electronegative, which means H2SO4 will be a stronger acid because the S and all the O's will pull electron density away from the H. So H2SO4 is stronger than H2SeO4. Okay? And the least strongest of them all is the one with 3 oxygens, which is H2SeO3. So H2SO4 is the strongest acid and H2SO3 is the weakest. So in this lesson, we will be learning about Lewis acids. Did you know that if you take CO2 and you bubbled it into water, it'll take that water and the CO2 will react with water and make it acidic? Okay, the same thing with our Earth. If you pollute the atmosphere with too much CO2, it'll make our lakes and oceans and bodies of water more acidic. The acidity will cause dissolution of shells. Okay, so, but that's weird. How can CO2 be an acid if it doesn't even have any H pluses? Well, that's because it's a Lewis acid. So Lewis acids are acids without the H pluses. Because we're not focusing on the H plus, we're now focusing on the electrons. Okay, so here's an example. BF3 is a substance that only has 2, 4, 6 electrons around it. The central atom only has 6. So it has an orbital that is empty. So do you see these 2 electrons from ammonia? It can donate electrons to the BF3. Because of that, it can make that bond right here. So this is actually a Lewis acid-base reaction where the acid takes in electrons. Okay, here, H plus. H plus is missing electrons, so the ammonia can donate to the H plus. Here, H plus is a Lewis acid as well. So the definition of a Lewis acid is that Lewis acid accepts electrons. And the way I remember it is AA. Lewis acid accepts electrons. Okay, so H plus is a Lewis acid. CO2 is also a Lewis acid because it will accept electrons from water, as you can see later. Okay, so atoms with empty valence orbitals can be Lewis acids. Okay, metals can also be acids because if it has a charge. So Fe plus 3, it's missing some electrons, so it can accept electrons from the water. And as you can see, the Fe plus 3 will pull electrons away from the water, allowing the H to leave, and makes the water acidic, makes the solution acidic. Okay? Lewis acids treats a wider variety of reactions, even if it doesn't have H plus. Okay? An example is CO2. It doesn't have an H plus, but CO2 is an acid. The way it does that is as follows. If you can see CO2 here, and the lone pairs on the water, the acid CO2 will accept electrons. Again, Lewis acid accepts electrons. As a result, you see the movement of electrons everywhere, and you end up with something called carbonic acid, or H2CO3. So this is why CO2 is an acid when reacted to water. Okay, so here's the equation. If you have CO2, you add water to it, you make H2CO3, which is acidic. It's acidic because this H can come off and become, so when H2CO3 gets rid of a proton, you're going to get plus HCO3 minus. This is the bicarbonate ion and what you have in baking soda, sodium bicarbonate, and this is called carbonic acid. Carbonic acid, and this is the bicarbonate ion. Okay, and again, the bicarbonate ion can give away another H+. Okay? So, what are Lewis bases then? If Lewis acid accepts electrons, then the Lewis base will donate. It's an electron pair donate. Will give the electron. In this reaction, the acid takes it. There's the acid. And the Lewis base will give the electrons. So ammonia is a Lewis base. And BF3 is a Lewis acid. And anything that could be a Bronsted-Lowry base is a Lewis base. Okay, so that means OH. Remember, OH is a Bronsted base because it can donate. See, it's a donor. It can donate electrons. Okay, so let's go ahead and look at the summary. We have three definitions of acids and bases. The first one, the oldest one and the narrowest one is called the Arrhenius acid and base. Arrhenius acid gives H, Arrhenius base gives OH. Okay? After Arrhenius, we have a bigger classification of acids. It's called the Bronsted acid and base. And a Bronsted acid accepts the H. So anything that accepts the H plus is an acid. No, oh, I'm sorry. Acid will donate the H. So H plus is Arrhenius acid, and base will take the H. Okay, so now we have more bases. OH minus can take the H, NH3 can take an H, OCl minus can take an H. Those are all Bronsted bases. In the beginning, Arrhenius base, we only have one kind of Arrhenius base, which is OH minus. Now we have more bases, Bronsted bases. We have OH minus is 1, NH3 is 1, OCl minus is 1, and there are more. Okay? Now the Lewis acids focuses on electron pairs. Lewis acid accepts electrons. So an example of a Lewis acid is H+. That accepts electrons. It's also a Bronsted acid. It's also an Arrhenius acid. But now you have more acids. BF3 can also be an acid. It's a Lewis acid. CO2 is also a Lewis acid. Okay, now the base is any substance that will give away electron pairs. Over here too in Lewis acids, metal ions can be Lewis acids too. Okay, now the bases. You can have a base that gives away electrons. OH minus can give away electrons. NH3 can give away electrons. And that's it.